Hey there everybody, and welcome to a short video introducing Chapter 6 on mathematical induction. This will be our fourth and final proof technique of the course. And this technique is sort of a classic way of proving statements about the positive integers. So we're going to prove things that look like for all positive integers and n something. So an inequality or an equation. Here's a statement about divisibility, saying that 4 divides any power of 5 minus 1. You can also prove statements about things as different as games. So if you don't know what the game Chomp is, that's totally fine. We'll talk about it later, not in this video. But basically, it's played on an n by n board, where n is a natural number. And you can prove using induction that the first player can always win this game. So induction is used to prove things like this, generally speaking, positive integers. We will see a few exceptions later, but mostly things like this. Equations, inequalities, or any sort of statement that can be phrased over the positive integers. I should say that this proof technique takes the most getting used to, I think, of the techniques that we will cover. But once you master it, it's really beautiful and really powerful, really elegant, I think. So if you talk to students who've taken this class previously, which I have not done a complete census or something of those students, many of them will tell you that this is their favorite technique because of how sort of, like I said, there's something very satisfying about the way the proof fits together once you master it. It's a really beautiful technique. So let me give you a broad overview of how the technique works without any technical details, and then I'll give you a formal definition later. So to motivate the technique, imagine a staircase with infinitely many steps, and I want to prove to you that I can reach any of the steps. And so, of course, put aside physical limitations for the moment. So in class, all of you have seen, my old man physique and have thought to yourself, I bet he can't climb any steps. So we put that aside for now. And if I want to justify this claim to you, there may be many proof techniques I could use, but consider this kind of argument. Suppose I could prove these two things to you. Suppose I could prove to you that I can reach the first step. So the first step is okay. In inductive language, that's called the base case. So I can get myself moving, is all I'm saying. I can at least get on the staircase. And then suppose I could prove this to you, that if I were on the kth step, I am able to reach the k plus first step. Suppose I could prove 2 to you for any positive integer. Then I claim to you that I have now provided a proof that I could reach any step that I want. And why? Well, basically, 1 and 2 combined here set off a chain reaction where, once I can reach the first step, once I'm on the first step, if k is 1, then I can reach k plus 1, I can reach the second step. But then if this item number 2 is true right here, once I'm on the second step, I can reach the third step. Then once I'm on the third step, I can reach the fourth step. So as long as I can prove to you that I can start this process, the base case means I just get the process started, and I can keep the process going as long as I want, I will have justified to you that I could reach any step. So this is saying if I'm on the k step, I can get to the next step. If I could do that for any k and I can reach the first step, those two things combined should convince you that I could actually reach any step that I want. So if I want to reach the 100th step, like I said, I know I can reach the first step, from the first to the second, from the second to the third, and so on. So broadly speaking, that's how this technique works. So if you think of the infinitely tall staircase as each step being some statement involving a natural number, so if you're trying to prove things like this, so think of the nth step as being this equation, but for that n. So the 5th step, put a 5 right there. The 20th step, put a 20 right there. If I could prove to you that I could solve this equation or justify this equation as true for any of those steps, I could sort of set off a chain reaction and justify the equation to you for any natural number. That's broadly speaking how it works. So induction is often visualized as staircases. It's also described informally as dominoes. So if you don't like the staircase analogy, a domino analogy is also used pretty often. So if I want to prove to you that all of my dominoes will fall in an infinite line of dominoes, I could justify to you that the first domino knocks down the second, and I could justify to you that the kth domino will knock down the k plus first. If I've justified those two things to you for any k here, then I've proven to you that all the dominoes will fall eventually. Okay, so that's an informal intro. Here is formally what the principle of mathematical induction says. It says, if you are asked to prove something like this, for every natural number, some statement, then you can justify these two things. As long as you justify these two things, then you've proven the theorem. So first of all, you can prove the theorem is true, or the statement is true, P of n. You can prove that statement is true for n equals 1. That's called the base case. So that's like getting yourself on the staircase. So first of all, you just prove that the statement is true for n equals 1, and that's usually straightforward because you just like plug 1 in here, see what statement you get, and hopefully it's true. So what's normally harder is this. You then need to prove this. If P of k is true, then P of k plus 1 is true. So this is like saying, well, if I've already reached the kth step, then from there, I could justify reaching the k plus first step. You would need to justify that for every k in n. This is called the inductive step, or the inductive hypothesis. This, assuming this, can you get to this? So if that's all abstract, I'm going to show you one example. I am well aware that introducing this in a video is not optimal. So I'm going to show you one example to get you the flavor of this. And hopefully, by giving you a flavor of this, your brain will be primed so that when we get back to class, it will flow more naturally. So I'm under no illusion here. You're not going to understand this technique super well after just this one example. But hopefully this kind of primes your brain and gets your feet wet and other body parts. It's only so many analogies I can come up with. Anyway. Okay, so here's an example. Suppose you are asked to prove this, that 2 to the n is always at least n plus 1 for every natural number. So this has the form for all n and n, P of n. There's your P of n. And you're asked to prove that. Notice none of the 3 previous proof techniques we have are great for this context. So, I mean, I guess a direct proof you could, there's nothing to assume here though, really, right? Like, what would you assume to get yourself going? Proof by contradiction, you would have to say this. Well, suppose there were some whole number such that 2 to the whole number is less than that whole number plus 1. And then you would have to derive a contradiction from that. That seems pretty hard. I don't know what you could get contradicted that way. So on. You can't use contrapositive because there's no if-then. So all of that to say, our previous proof techniques kind of hit a wall right here. Just, hey, prove this. You know, maybe there's a direct proof. I don't know. Anyway, so to use induction, you just justify these two things. So first of all, ask yourself, is the statement true when n equals 1? So when n equals 1, 2 to the 1 is indeed bigger than or equal to 1 plus 1. So that's the base case. The base case is usually straightforward, where you just ask yourself, if I plug in a 1 into my inequality or my equation or whatever, do I get something true? And in this case, we do. So we've now like gotten ourselves on the first step. Now, of course, we can't just keep verifying like this. We can't just be like, oh, and notice 2 squared is bigger or equal to 3. That's true. And what, 2 to the third, that's bigger or equal to 3 plus 1. And so, of course, you can kind of see that it's true by plugging in different n values, but that's not a proof. And we can't just keep plugging in values for n forever, right? We'd run out of time. Okay, so now what you do is, you have to now prove this. If P of k, then P of k plus 1. So you're going to prove this. So what that means is you assume P of k, and then explain why P of k plus 1 follows. So whenever you want to prove an if-then like this, a way you can do it is to assume this, and then justify this. Okay, so let's see how that works. So now we'll assume that this is true for k, and then we need to justify why this is true. This is the inductive step. You assume whatever you're trying to prove is true for k, and then use that assumption to justify why it's true for k plus 1. So again, this is the statement for k. There's the next step, k plus 1, subbing in a k plus 1 for n. Right, there's your n, there's your k plus 1. So this is how induction works. It's like it's proving that if I manage to reach this step, like the kth step, then I'm able to reach the k plus first step. That's what's happening here. So you're setting off a chain reaction. And the chain reaction goes all the way throughout the naturals because k is arbitrary here. So k could be 100, k could be 2 billion, whatever. If I'm on the 2 billionth step, like if I know this formula is true for 2 billion, then I'll now justify to you why it's true for 2 billion plus 1. Okay, all of that to say, once you assume this, your goal is now to justify this, p of k plus 1. So we're allowed to take this inequality here, this kth inequality, as a given. We're assuming it. And we want to now use that to justify the k plus first. And so now you're back in basically chapter 3 or something. If I give you this, and I say, well, can you use that to justify this? You just do whatever you need to do to get from point A to point B. So if you have this inequality, and you want an inequality with 2 to the k plus 1, then just multiply both sides by 2. So there you go. There's a 2 to the k plus 1 now. Twice k plus 1. And that inequality is the same thing as 2 to the k plus 1 is bigger than or equal to 2k plus 2. And so the thing is, though, we're trying to justify why 2 to the k plus 1 is bigger than or equal to k plus 2. Well, we learned right here that 2 to the k plus 1 is bigger than or equal to 2k plus 2. Well, 2k plus 2 is certainly bigger than k plus 2. And so we have now taken this inductive assumption here that the theorem is true for k, and we've justified why the next step would necessarily follow. So we can get from this assumption to this. That's what an inductive proof looks like. Like I said, it does take some getting used to, and sometimes when you're done, you're like, wait a second, what did I prove exactly? So I was supposed to be proving that 2 to the n is bigger than or equal to n plus 1. Did I do that for all n? Is that something I did? And the answer is yes. So let's just briefly discuss, why is this a proof? Why has this inequality been justified? Well, first of all, I just verified it for n equals 1, so you can't argue there. Right? Nobody's going to argue that 2 to the 1 is bigger than or equal to 1 plus 1. So we got that. I also showed this, though. I showed that for any k, 2 to the k bigger than or equal to k plus 1 implies 2 to the k plus 1 is bigger or equal to k plus 1 plus 1. So I showed that if the statement is true for k, it must also be true for k plus 1. And I did that for any k. So just in concrete terms, what that's saying is, well, if you know it's true for p of 1, you know it's true for p of 2, because the case statement implies the k plus first. But if p of 2 is true, well, p of 2 now it would imply p of 3, because again, I justified up here, if it's true for k, it's true for k plus 1. So p of 1 gives you p of 2, because we showed this implication that p of k implies p of k plus 1. P of 1 gives you p of 2, which then in turn gives you p of 3, which then in turn gives you p of 4, which then in turn gives you p of 5, and so on. This and so on just ripples through the natural numbers. So like, how do you know, for example, that 2 to the 1,000th power is bigger than or equal to 1,000 plus 1? How do you know that? Well, because this chain of implications reaches anywhere inside the natural numbers. So 1,000 here would be like your 1,000th step, and I proved to you that I can get to the first step, the base case, and then I proved to you from the kth step I can reach the k plus first step, and I can do that for any step. So that is how proof by induction works. I'm only showing you one example because I think in a video there's kind of diminishing returns of showing you an example, but in class we will do all of these and more. So this is basically the entire chapter, using induction to prove things like this. And like I said, it definitely takes some getting used to. So we are going to spend multiple days. I hope we have time to have a day where you just work on induction problems. But also, like I said, I think it's worth it to master this. It's a very powerful, very elegant. I mean, look at this. Very nice. So if you don't like it now, I'm going to insist that you learn to appreciate it by the time we're done with chapter 6. It's a proof technique tailor-made for just dealing with statements over sets like this, the natural numbers that have some ordering to them, where the space in between the numbers is the same. So the naturals are evenly spaced. They're kind of like dominoes. So whenever you have a set like dominoes, you can hit it with induction to prove inequalities or equations or things like that. Okay, so that is the end of this sort of intro to induction. If you have any questions on this or whatever, feel free to email me before I get back. But then when I get back, we can discuss this example and others.